Hey everyone, welcome back. And we're moving on to question number 21 in the 2019 BEAD test. The question reads, an empty freight car on a level railroad track has a mass M. A chute above the freight car opens and grain falls down into the car at a rate of R, measured in kilograms per second. The grain falls a vertical distance h before hitting the bed of the freight car without bouncing up. How much normal force is exerted on the freight car from the rails at a time t after the grain begins to hit the bed of the floor of the car? Assume the grain starts from rest. So we're looking for the normal force, which is equivalent to the force on the grain by the car, right? So, or just the total mass on the car plus whatever other forces the car exerts. So obviously the normal force has to include mg of the car. All the answer choices include mg, so that doesn't really help us. And now let's think about how much grain actually is on the car after time t, after the first grain hits the bottom of the car. So we can imagine that if the time it takes, so if a grain is dropped at time 1, at time 2, time 3, time 4, time 5, so this is when the grain is dropped, and the grain will hit the ground after a time given by delta h, so whatever height the car is equal to 1/2 g t squared, right? So it'll be 2 delta h over g. The square root of this is the time that it takes for it to fall through the air and hit the ground. But notice that each one of these will be adding the exact same time onto it, right? So basically, the time that it takes for it to hit the ground, let's see, ground is equal to the time for it to fall plus this time that it spins in the air. But you can imagine that the time that it takes for consecutive grains to fall, so t, let's call this t ground 1 and t fall 1, and then t ground 2 is equal to t fall 2 plus this exact same constant. If we subtract these two, which gives us the rate at which it falls down to the ground, right? We just get the same rate, which is t fall 2 minus t fall 1. So t ground, let's call tg1 minus tg2 minus tg1. So the constants cancel out, which means that also it's hitting the ground at a rate of r, okay? So that means that after a time t, r times t of mass is actually on the bottom of the car, right? So that amount of weight is also the normal force that the freight car must exert upwards. So we might think that this is our answer now. The answer is A, right? However, we forgot one crucial detail, which is that the grain is falling down, and it has the initial velocity when it's falling down, but then the car must exert a normal force upwards in order to cancel out the momentum that the weight of the grain has, right? And we need to add in, so that means we need to add another force that the ground needs to exert on the grain. How do we find that? Well, this question, if you do enough of these questions, it kind of reminds you of a momentum question. So basically, you have the momentum, the change in momentum is equal to, so mass times velocity, the change in mass times velocity, right? So the velocity, so the mass that is hitting the ground after a time t, so that's after times t, that will just be r delta t, right? That's the mass that will hit the ground after a time t. And what's the velocity? The velocity is actually just changing from the initial velocity that it's at all the way to 0. So the velocity that it has when it's falling right before it hits the ground is the change in velocity, right? So this is the change in momentum. Now remember that change in momentum over change in time is equal to the force, right? So if we divide by change in time, we get RV, right? This delta t just cancels out. And this velocity, you can really easily calculate just from, what's it called, conservation of energy. So 1/2 m, sorry, 1/2 mv squared is equal to mgh, right? So the m's cancel out. V is equal to 2gh, the square root of 2gh. So if we plug that back into here, that gives us r times the square root of 2gh. And this is the force, actually, that it must always exert at any time, because of the fact that it has to continually bring this much mass down from its initial velocity to velocity 0. And that means that it actually gives us this as the final answer. And you can just see that this makes sense because as time goes on, there's more grain on the ground, so this thing continually gets bigger. But this value always stays the same because the force that is required to keep stopping the grain is only dependent on the rate that the grain falls down. It's not dependent on how much grain is left on the car at that time, right? So that's the final answer.